In this video, I'd like to talk about the math question of the day for Saturday, August 5th, 2023. And with this problem, we're given a function f of z, and we need to determine the function's critical points. So this topic of critical points is something typically taught in a Calculus 1 class. And at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And before we look at the specifics of this problem, let's consider what critical points actually are. So if I draw a quick coordinate plane here, we can look at some random function. And critical points, graphically speaking, are typically the maximums and minimums of a function, but they can also be something else. So this point right here, the maximum or a local maximum, this would be a critical point. This local minimum would be a critical point. We have another local maximum. And we have this point right here where it might not be obvious how I drew this, but you can imagine this as a very distinct point, like you get with the absolute value function. Remember when you graph y is the absolute value of x, that it comes in at a point at the origin. So this function, it exists at the origin, but its derivative does not exist there. And the overall definition of a critical point is that it's a point where the function exists and the derivative at that point is either equal to 0 or it doesn't exist. It's not defined there. But the function has to exist there for it to be a critical point. For instance, with this function, there will be certain z values that let the denominator equal to 0. Those points will not be a part of the function, and so therefore they cannot be critical points, even if they meet these conditions once we find the derivative. So our goal here is to find the derivative and figure out when that's equal to 0. And remember with these critical points, the reason that we end up with the local maximums or minimums as being the critical points is that we're considering the derivative. And remember, the derivative measures the rate of change of the function, or it tells us the steepness of the tangent line. So if we were to draw in lines that are just tangent to a given point, you can see that that steepness will change as we move along the curve. And at a maximum point, notice that the steepness of this line is 0. Or we can say the slope, m, of this line is 0, meaning that the derivative is 0 at that point. And then you can see that the slope of the tangent line gets negative, gets more negative. Then it starts going back to positive, starts increasing, and then here at this local minimum, it again reaches a flat tangent line. And then after that will increase to positive slopes. But again, getting to this local maximum, we'll see that the tangent line again there is flat, meaning that the slope is 0 or the derivative is 0. So it's these points where the slope of the tangent line is 0, it's a flat tangent line, or it's these points that don't exist at some type of cusp or corner here, where there's no real way to draw in a tangent line. You can't draw it flat like that, but you can't logically define it like this or like that either. There's no way to define what line would actually be tangent at a point like this, which is part of the reason why the derivative won't exist there. So now that we have an idea of what a critical point is, we just need to find the derivative of this function. And since we have a quotient, we can use the quotient rule. If we have a function f over g, where f and g are both functions themselves, we find the derivative, then this is equal to the derivative of the numerator multiplied by that denominator function. And from there, we will subtract the derivative of that denominator function multiplied by the numerator function. And then all of this is divided by that denominator function squared. Now let's apply that to our function here. We want f prime of z. We want the derivative of the numerator function, the z plus 4, which will just be 1. Since we're using the power rule, we just bring the 1 down in front and subtract the exponent by 1. So we get 1 times z to the 0, but z to the 0 is 1. Then we multiply by that denominator function, which is 2z squared plus z plus 8. Then we subtract the derivative of that denominator function. We use the power rule, bring the 2 down in front. 2 times 2 is 4. And we subtract that exponent by 1. Then for this term, it's to the first power. We bring down the 1 in front. And we multiply by z to the 0, which we know is 0. And the derivative of a constant is 0. Then we multiply all of this by that numerator function, z plus 4, and divide everything by the denominator function squared. We have 2z squared plus z plus 8, and then all of that squared. So this right here is our first derivative of the function f with respect to z, and to find its critical points, we'll just set this equal to 0. So let's make a little bit of room, and we can start simplifying this. Let me just rewrite what we have in our numerator here. We will distribute this 1, so that won't change anything. And I'll leave the denominator as this 2z squared plus z plus 8 squared. And for our numerator, we're distributing the 1, so we get 2z squared plus z plus 8. Then we need to multiply these together and subtract them. So we distribute 4z times z, that is 4z squared. 4z times 4, that is 16z. Then we get plus 1z and plus 4. Now let's actually carry out this subtraction here. We'll distribute that to all of these so that in our numerator we get 2z squared minus 4z squared, which would be minus 2z squared. We get plus z minus 16z minus z, so that would just be minus 16z. And then plus 8 minus 4 would be positive 4. And again, we can just rewrite this denominator. And to find these critical points, we know we're setting this equal to 0. And this expression will equal 0 when the numerator is 0. Now, at that same point, the denominator can't be 0 at those same values. But these are different quadratics, so we're not going to run into that issue. So we can get critical points by setting the derivative equal to 0 and then finding solutions to that. We can also get critical points from when the derivative does not exist. And there are values when this derivative does not exist, when this denominator is equal to 0. But the critical points, remember, occur when the function exists and either the derivative is 0 or the derivative doesn't exist. So the first method for finding those critical points is just setting it equal to 0 and then solving. But with the second method, we need to be a little bit more careful. We need to find when that first derivative doesn't exist, meaning we would need to figure out when this denominator is equal to 0. However, that denominator of our derivative, notice, is basically the exact same denominator of our original function. The only difference is that this is squared. But it doesn't matter. The main idea is that the denominator will equal 0 at the exact same values. Since if this simplified to 0, like in our original function, then in our derivative here, if we square it, then 0 squared is still 0. So the square doesn't affect the zeros of that denominator. So in other words, if that was a little bit confusing, we don't need to look for when the first derivative doesn't exist, since it's the exact same values that the original function doesn't exist at. And if the original function doesn't exist at specific values, then it can't have critical points there. So the values that the function doesn't exist at would be the same values that this derivative doesn't exist at. So we don't need to actually look for those because those cannot be critical points because, like I said, the original function is also not going to be defined there. But if you want to see what those values were, we would just use the quadratic formula on this and we would actually end up with some complex numbers. But they are not critical points because the function's not defined there. So with all that being said, we really just need to check this numerator here and figure out when that's equal to 0. And to do that, we'll just set it equal to 0 and solve. We have minus 2z squared minus 16z plus 4. We're wondering when this is 0. And let's start by just dividing everything by -2. It's z squared plus 8z minus 2 is equal to 0. And this we can use either factoring or the quadratic formula. And it doesn't look like factoring would work easily on this, so let's just use the quadratic formula. So we want the opposite of b. Remember, we have az squared plus bz plus c for that quadratic formula, though usually you see it with x, but it doesn't matter. The coefficient on the linear term, we take its opposite. Then we put plus or minus the square root of b squared. So we have 64 minus 4 multiplied by a, which is 1, times by c, which is -2. All this is divided by twice a, or 2 in this case. And we can simplify this. We have -8 plus or minus square root of 64 plus 8, which would be 72, all over 2. And we can simplify the square root of 72, since 72 can be broken up into 9 and 8. 9 is really just 3 squared. 8 is 2 times by 4, which of course is 2 squared. So we can separate this and simplify it, since we do have perfect squares under here. This would be root of 9 times 8, or the square root of 9 multiplied by the square root of 4 multiplied by root 2. And we separate it like this because we can actually find square roots of 9 and 4. This is 3, this is 2, so we get 6 root 2, meaning that this simplifies to -8 plus or minus 6 root 2, all divided by 2. And we can divide them each by 2 so that we get -4 plus or minus 3 root 2. So this right here, these should be both of our critical points for our function.